So welcome back. Problem 2-4. Let's just start from the first part here. A, we want to find the density of X. What is the density of X? Now what I'll do here is just come up with the intuitive solution first. So the density of X, we denote that by Fx of little x. Then I'll write equals to. Well, we know that depending on the storm strength, X will have different densities. And if the storm strength is 1, X will be exponentially distributed with the parameter lambda 1, which kind of then tells us it makes sense to think of it as with probability 1, X has distribution given by the exponential distribution with parameter lambda 1, which has density as such, where I plug in lambda 1 instead of lambda. So there is a probability P1 that the density of X will look like this. And let's just write for X greater than 0, because then we don't need to write this indicator up here again and again. So with probability P1, the density looks like this. Now with probability P2, the storm has strength 2. And in that case, X will have the density lambda 2 multiplied by e to the minus lambda 2x. And with probability P3, X will have the density lambda 3 multiplied by e to the minus lambda 3x. And then we can kind of ask ourselves, well, is this a valid guess? Because does this even make sense? And we're not really sure of this yet, but there is one thing that we can check just to know that we're not completely off, that we're not completely off here, is what happens if I try to integrate this entire thing over the real axis, because we know that all densities need to integrate to 1. So let's just check that out for a moment here inside a little box. So what happens if I decide just to say I want to integrate the density of X from 0 to infinity? And it's okay just from 0 to infinity because the density is 0 below 0 here. So let's see what happens. Well, then what happens is I will have P1 multiplied by the integral of lambda 1 e to the minus lambda 1 x dx plus P2 multiplied by the integral from 0 to infinity of lambda 2 e to the minus lambda 2 x dx plus P3 multiplied by the integral from 0 to infinity lambda 3 e to the minus lambda 3x dx. Now we'll end up going a bit outside of the box, but that's okay. What we see here is I have P1 multiplied by the integral of a density that is concentrated on 0 to infinity. So this is just equal to 1. And this integral is also equal to 1. And this integral is also equal to 1, because in all three cases I just integrate an exponential density. So essentially what I have is P1 plus P2 plus P3. And that is very nicely equal to 1. So at least this density does integrate to 1. So that was the least that we could check. And if I should write this up a little bit more nicely, we have that the density of X is given by Pi multiplied by lambda I e to the minus lambda I x, summed for all three cases, I equal 1 up to 3, where x is greater than 0. So this is kind of our first guess for the solution of A, and in the next video we will then show that this indeed does make sense. But just intuitively, what we do is we say, well, depending on the storm strength, x will have different distributions. So we just take a weighted average of the different densities and add them together as such. So this is the intuitive answer for part A.